So, last class we have taken one example for a nonlinear programming problem that f x is equal to 4 1/3 x 1 plus 1 whole cube plus x 2 subject to this constraint, and we have to solve this problem by using exterior penalty function method. Then we have seen this one that x 1 is greater than 1 and x 2 is greater than equal to 0. These are the feasible region. So, initially we have to form a penalty function method with the objective function and with the constraint like this way. Once you form this one, then your job is to find out the necessary condition for the function to be optimized. That we have seen it that first this is the analytical solution by finding the necessary condition del p del x 1 del p del x 2 is 0. So, after solving this after details expression for 1 and 2, we will get a set of 2 simultaneous equation, and our job is to solve this one, and ultimately after solving this one we got x 1 value with this expression. But you have to take proper sign of when you are finding out the roots of this quadratic equation of that one, you have to take the proper sign of this one, because x cannot be negative because of feasible region solution. So, that plus you have to consider this one where this plus this term is greater than this one, that we have explained last class. Similarly, x 2, when you solve this x 2, you have to take proper sign change, but our x 1 x 2, if you see this one x 1 x 2, our things should be a what is called that in the x what is called infeasible solutions, is it not? Because infeasible solution, exterior point mean infeasible solution we are taking, and then we are finding out the function value, which is function value is decreasing with each iterations, and ultimately it will converge to a some optimum value of the function which is a feasible. So, that we have seen and we have got the results, this one x 1 is equal to 1, x 2 optimum value is 0 when tau k, that penalty coefficient, tends to infinity. Let us solve this problem by using what is called iterative method, because we are using the necessary condition expression, necessary conditions what we got it x equation number 1 and 2, we express x 1 and x 2 in terms of tau k. Okay. And now tau k I will change from small value to very large value, the infinity, and if you use the iterative method, how you will solve this problem, that we will see using the iterative method. That is, we are considering the exterior point, exterior penalty function method. The same problem, whatever the we got the necessary condition for this problem and express x 1 in terms of tau k, x 2 in terms of tau k, that we are writing now. So, our iterative method, we make the tabular form, and this is the tau k penalty coefficients, then we will expression for analytical function expression for x 1 of k, k superscript k indicates iteration, which expression we got it 1 bracket minus 1 plus tau k, see the expression, plus root over tau k square plus 4 tau k under square root, then x 2 k is equal to minus 1 by 2 tau k, then penalty function value you write it, which is a function of x superscript k into tau comma tau k, and then you find out the f, if you like you can find out x of k, capital X of k, then you can function value f of x superscript of k, this. Note that our f of x, small f of x is equal to 4 1/3 x 1 plus 1 whole cube plus x 2, this is our f x, and capital F x, x of superscript k is equal to max 2 1 minus x 1 0 this, then whole square for G1 constraints, and for another constraint max minus twice x2 comma 0 max of this and this square. So, this is our axis. Let us calculate this one. First we start, let us have small value of tau k 0.001, then this value, put the value of tau k here in this expression, you will get this value is 0.9377. Then x2 1 by this, if you put it this value, you will get minus 500. And once you know x1, x2, that function value you can compute. That function value is minus 2000. Then once I know x1, x2, f of x I can compute. That value will be 100,000.02. So, what is P? This multiplied with this is multiplied by tau k, also I included tau k. Mind it, this is also I have included tau k and got it. You can find out only f k, but I multiplied this tau k into f of k. Tau k into f of k is that one. So, this, then this is equal to what? This minus tau k of this one that P, then you will get this value is this, then tau k, see this expression, that what we have written it, that P expression f of k tau k into this whole thing is capital F of k. So, this and this you add it, this and this if you add it, you will get it minus 999.98. The next choice of tau k is 10 times of this one, that is 0.1 if you take, because lambda k for exterior point method, if you recollect, lambda k plus 1 divided by lambda k is equal to c. C is greater than 1 and we say that c value is 10. So, next is this value, if you put this value is this, you will get 0.809 minus 50, then you will get f is, you will get minus 1.199.99, then lambda k into f of x is here, f of x I know, multiplied by lambda k, you will get it, this value is here, that is you are getting 100.13, then this plus this will be your 99.86, but minus sign again. Again 10 times of this one 0.1. You see the function value is decreasing, 2002 now it is coming near about 200, minus 200. So, next value is this is 0.04597 minus 5, and this value will be 19 point minus 19.79, and this value will come 10.85, because when you put these values lambda x1 x2 value here and multiplied by lambda k, this value is I am representing here. So, this plus this will be minus 9 minus 8.938. So, now if you proceed like this way and increasing the value of lambda k, you will see at 1, 2, 3, 4 up at 10,000, lambda k value is 10,000, the value what you will get is the x1 value by applying lambda k here, x1 value will come 0.99963, then x2 value will come minus 0.00005, and f of x value will be coming is that is 10.661, and lambda k into f of x value is coming 0.00012. So, that value will coming, this plus this is equal to 10.662. Now, this see this point, our feasible region is x greater than equal to 1 and x 2 is greater than 0, but both are not satisfied this one, still it is a infeasible region. So, we need further more iteration. If you go on iterative like this, so a very large value of lambda, let us call say infinity, then this will get 1, this will get 0, and this will get, this value we will get it here 32 by 3, this is 0, then this is 32 by 3. So, this contribution of the penalty function is become 0 when it reaches to the optimum value of the function. So, our optimum value of the function is 32 value 32 by 3, and corresponding optimum point is x 1 is 1 and x 2 is 0. These are the optimum point for which the function value is this. So, this we have, and you see even though these 2 points still is not in interior point, it is a exterior point still interior point. And since we know the our feasible region x 1, if you see the feasible region x 1 is greater than equal to 1 and x 2 is greater than equal to 0. So, both condition is not satisfying. So, it is not an interior point of that one. So, next we will see some of the problem associated with this one, or you can say more general expression. We will discuss the problem later for general form of that one, that how to solve the problem using that what is called exterior penalty method, penalty function method. We have seen that minimize the function again subject to inequality constant. Suppose if you have a equality constant, then how to tackle that problem. So, it is a general form of nonlinear programming problem using exterior penalty function method. What sense I am telling you? We have not considered the equality constant. So, our problem is like this way. This is the minimize f of x subject to h I of x is equal to 0, and we have a such equality constant, p equality constant is there, and equality constant x j of x is less than equal to 0. We have m equality constant. Now, how to introduce this one? So, this one can write it, there are two ways of doing. One can write it h I of x 0, this one can write it into a inequality constant h I of x greater than equal to 0, h I of x is less than equal to. So, this equality constant I can write it this, and we can solve similarly as we have discussed earlier. Okay. So, in each equality constant we get it two inequality constants. Okay. So, in turn we will get 2 p inequality constant, and there is already m inequality constants are there. So, there will be a m plus 2 p inequality constants we will get it. But in generally we can write penalty function penalty general penalty function we can write it. So, this p which is a function of x tau k and beta k. Tau k is penalty coefficient associated with the inequality constant, and beta k is the penalty coefficient associated with the equality constants. So, this equal to, now we are writing objective function as it is, plus beta k summation of all 1 to p equality constant h I of x, this whole square, that is just like a inequality constant we used to do gamma k summation of j is equal to 1 to p, then we used to write it max of this, max of g j comma 0 whole square. In place of this one it is j of j s square plus gamma k summation of j is equal to 1 to m max g j of x 0 whole square, and this is, let us call, equation number 1. And these are, this and this are the penalty coefficient gamma k tau k, let us call, we have written tau k through this one. Tau k is the penalty coefficient associated with the inequality constant, and beta k is the penalty coefficient associated with the equality constant. Both quantity is greater than 0. Okay. So, we make some comments of this one, that now how to choice of initial values of penalty coefficient. That means tau k and beta k. One of the simplest choice is there, you consider a point which is outside the feasible region, that is called the exterior point. Then beta k, selection of beta k, initial choice of beta k. After that, what we are doing? We are incrementing, we are increase the value of beta k or gamma k by 10 times. So, initial value of beta k penalty coefficient associated with the equality constant, and tau k associated with the inequality constant, how to select it. So, that value is, so objective function value, then penalty terms value corresponding to equality constant. Penalty terms, because we have a penalty terms associated with the equality constant, we have a penalty terms associated with the inequality constant. So, this penalty terms, then tau k is objective function value. Similarly, then penalty terms value corresponding inequality, corresponding to inequality constants. Values corresponding to this. So, this initial value we have to select. This is the one choice of this one. Next is one remark, important remark is there, that analytical solution, that what we did it, that we, in order to find out the what is called first the initial that necessary condition we have found out. Then we have solved this problem for x 1. The solution, we have solved this two set of equation, or in general n set of equation, by x 1, x 2, all decision variable we have calculated in terms of our tau k, and for our present problem. In now you have it x 1, x 2, everything you have to express in terms of tau k and beta k, but it is really very tedious job to get such an expression. So, we have to look for what is called the numerical method solution of a set of equation which is obtained, set of equation which are obtained from the necessary condition of the problems. So, let us, what is this? I just mentioned in this one, remarks of this one. For a general nonlinear programming problem, there will be n equations, because if the nonlinear problem is a n decision variables are there, then when we are taking the necessary condition, that after forming the penalty function del p with respect to x 1, del p with respect to x 2, we have a x 1 x n variables are there. So, we will get x n equations given by, from where you will get it, the gradient of penalty functions x The penalty function is a function of tau k and beta k. To be solved, and there will be m max term in each of these equation, in each of these equations, because we have a m inequality constant, and in if when you have a inequality constant, m inequality constant in penalty function, you will get summation of max term of g1 comma 0 whole square, then g2 max of g2 comma 0 whole square. In this way m terms will be there each equation. Again, it is almost, that is what is the main stress thrust is there, it is almost difficult to express xi, which is a function of tau k beta k for I is equal to 1 to dot dot, because we have n decision variables, and then take limit tau k tends to infinity, very large value, and beta k tends to infinity, to get optimal solution of the decision variables x1, x2, x3 dot dot xn. So, one should look for what is called the numerical method to solve a set of necessary conditions. If you have n decision variables are there, you will get set of n nonlinear algebraic equation that you can solve by some suitable numerical methods. That is our stress. So, therefore, it is necessary to solve equations del p of x tau k beta k is equal to 0, that is the necessary conditions, using some numerical methods techniques. So, this is the remarks for this one. So, next we will solve that what is called nonlinear problem, solution of nonlinear programming problem using interior penalty function method, or it is called barrier function method. So, next is solution of, next topics is solution of nonlinear programming problem using interior penalty function method, or this is called interior penalty function is method called is a barrier function method. So, what is this? We will see first. If you recollect this one, our earlier problems, the exterior penalty function method generates a sequence of infeasible solution that converts to a feasible solution. In exterior penalty function method generate a sequence of infeasible solution which converts into a feasible solution, okay, and optimal solution. Whereas, in case of what is called interior penalty function method, it generates a sequence of feasible solution and ultimately it converts to a optimal solution, feasible and optimal solution. So, this is the difference between the two methods. So, exterior you can write the interior point method, interior penalty function generate a sequence of feasible points that converges to a feasible and optimal solution. That means x n x superstar of this whose dimension is n cross 1 and if it is a n BCD problem. So, our problem is we have a problem minimize the function subject to the constraint, agree. Then interior point method generate a sequence of first initial guess is the interior point in the feasible region, then it generates another feasible point where the function value is decreasing, and in this way it generates a sequence of feasible points and ultimately it converts to a feasible and optimal point, optimal solution. So, let us see this one, the problem statement, how we will do it. So, minimize f of x is the objective function, you have to minimize such that g j of x is less than equal to 0, j is equal to 1 2 dot dot m. Okay. So, this is our problem. Now, we have to solve by using a interior point method. Okay. The interior point method means we have to take a initial guess which is inside the feasible region and satisfy all these things. Feasible region means it should satisfy the what is called the all types of constraints. So, corresponding to this you problem construct the following interior penalty function, or it is called interior barrier function. Barrier means obstacle function, barrier always is we understand the obstacle function, in the sense that it will not allow to move the decision variables boundary of the feasible regions, it will not allow to cross the boundary of the feasible regions. So, now let us see this one, what is the penalty function is considered for this one. So, P x tau of k is similar as earlier also exterior point method f x plus tau k, and tau k is our penalty coefficients. Since we have a m inequality constraint, we have to give the penalize this one is j is equal to 1 to m minus 1 by g j x. Agree? Now, look this one, our point is interior point, means point is inside the feasible region. When it is a feasible region, g j of x value is negative. Agree? When it is negative, negative is a positive. So, this quantity is positive. So, that means this quantity and also tau k value is greater than this tau k value is greater than 0. Okay. So, this is our let us call equation number 2, and this set of equation what about the description of the problem, it is a equation number 1. So, this term is this whole term is penalty function term, this is this and this is the penalty function term, penalty function terms. So, with tau k plus 1 next iteration tau k value will be is equal to c, where c is less than equal to 1, say c is equal to 0.1. Now, we are decreasing the penalty function value, penalty coefficients value 1/10 each iterations. So, let us see the interpretation of these things. Why the tau k value will be decreasing and ultimately it is approaching to 0 to get the optimal solution of the problem using interior penalty function method. Let us take this simple example. Minimize x such that or subject to 2 minus x is less than equal to this. So, this implies x is greater than 2. So, our feasible region is x greater than 2. If I plot it, this x is in these directions and this direction is our penalty function p, penalty function in these directions. If we plot it, then let us say f of x is what first. F of x is what is nothing but a x, and that f of x you have to minimize. So, this is nothing but a straight line which is passing through a origin, and our feasible region is, if you see our feasible x greater than 2. So, let us call this is 1, this is 2. So, greater than 2. So, our whole feasible region is that portions. So, this is x is equal to 2, this is 0, and this is, you can write it, this nothing but a f of x is equal to x, and with this one there is another function is added. Agree? So, our g of x for this one is 2 minus x. So, if you write it minus 1 by 2 minus x, and our initial guess is we are considered in the feasible region. So, the x value will be greater than 2. So, let us see when x is equal to greater than equal to, when x is equal to 2, the function value, if you see this one, the function value is x is equal to 2, it is very large, and then it will go on decreasing, and it will approach to this asymptotically, it will approach to the objective function values. So, this. So, let us call these values is, I am plotting is that this function value, that means our, in our case if you see the p, in our case if you see the p tau k is equal to f of x, means x plus tau k, only one inequality constant is that 2 minus x inequality constant is there. So, I will write it into minus 1 by 2 minus x. So, I am now plotting this quantity. Again, I am plotting this quantity. So, this value is infinity of that one, and then if you go on increasing x, then this value will be, it is negative plus. So, this will be this way, and it is approaching to the asymptotically, it will approach along the objective function line. Let us call, you can think of it as if that our penalty coefficient value is 1 when you are plotting this one. Okay. Now, if the penalty function value is made it half or 1/10, now what will be this? The nature of the curve will be exactly same, on only at each point of x the magnitude will be reduced by 1/10 if you are considering that tau k value is 1/10. So, this will be once again, if you see this one, once again this will be like this way. So, this is, let us call tau k value is 1, okay, and I am plotting, this is for tau k value, I am plotting g of 1 by minus, this is I am plotting 1 by g of k, g of x I am plotting. I am plotting tau is equal to 1, g of a, and this is corresponding to tau of k is equal to 0.1, and this is minus 1 minus g of x I am plotting. So, in this way, if you are reducing the value of tau k by 1/10 all these things, ultimately you will see this value will be decreasing, ultimately you will see this will be like this way. and it will be approaching along this one. Okay, and when when x is equal to 0, is you say when x is equal to when x is equal to 2, x is equal to 2 or nearly equal to 2, this infinite value is that this is right. So, it will not allow to cross the value of feasible region variables value cross the right left hand side of this one. That means, it will not allow the this method will not allow to cross the boundary level of feasible region, this method. So, that is why tau k value is slowly, if you increasing, it will approach to the asymptotically to the objective function near to the boundary of the feasible region. That is our main objective. So, I will just write it the remarks of that one. So, remarks. So, that is the basic idea of using the interior penalty function method. So, now remarks. If x is within the feasible region, in the feasible region or space for feasible range space and far away from the boundary, then g of x, g j of x is less than 0, and penalty term is small, and okay. So, penalty term is small and p x of tau k will be nearly equal to f of x. This is first, and second observation or remarks is when x moves towards the boundary, of the feasible space, when x is moved towards the boundary of the feasible space and constraints tends to tend to be binding or g j x will be 0, then the penalty function will prevent or you write that then the penalty function will become very large and preventing x from moving out of the feasible point. So, what we have discussed in this figure, you see the first statement is made when x is far away from this one, you see this quantity is large, that means 1 by this one is small, very small. So, in that situation penalty function value and objective function will be same, that is the we told that one. When the our variable x is closer to the boundary of that one, when it is closer to this one, okay, then this quantity value that 1 by x 2 value will be very large. That is, when x is moves towards the feasible region space tends to binding g x is equal to 0, then only this 1 by g x will be very large. Then penalty function will be very large and will prevent the what is called the variable to go to the infeasible region. So, moving out from the feasible point. So, this is the basic idea behind using the interior point method. So, our algorithm steps for interior point method, interior point function method. Same as earlier exterior point, first step is what? We will select a initial point which must be inside the feasible region. So, select a feasible solution or feasible point x superscript 0, and that must be an interior point that satisfied all constraints. That means, g j of x is less than equal to 0, j is equal to 1 to dot dot m, and choose and select tau 1 greater than 0 and k is equal to 1. This is the first step. Once you select this one, using the what is called necessary conditions, all these things, you find the new improved value of the feasible point, which reduces the function value from the previous value. So, second step, take x superscript of -1 as a starting point. Use unconstrained optimization problems, unconstrained minimization problem. If it is a minimization problem M, or you can unconstrained optimization problem. Use unconstrained minimization problem solution using numerical methods. So, our numerical methods we have discussed what is called Newton-Raphson method, steepest descent method, conjugate gradient method, modified Newton-Raphson method, we have discussed it earlier. So, taking the initial starting point, you get the first, you obtain the necessary condition for the function to be optimized, and you will get set of nonlinear equation that you can solve by numerical method or analytically. Use optimal solution, using unconstrained minimization problem solution using numerical methods to obtain, to find the optimum of barrier, optimum of the barrier function. Or interior penalty function denoted by x superscript k. From x k minus 1 you get it that one. Next step is step 3 is check if the solution is reached to the optimum. Check if the solution x superscript k is the optimum solution of the original problem. Okay, if the optimal solution of the original problem. How will you check it? I told you one way of checking it, you find out the value of the function at kth iteration, then subtract with k minus 1th iteration value divided by f of x k value. So, mod of this one, if you see, if it is less than equal to epsilon, epsilon is a positive quantity, positive small, very small quantity is this one, or you can check it this, or you can check it that tau k or f of x superscript k, that value is less than equal to epsilon 2. Epsilon 2 is less than greater than 0 and very small quantity. Tau k is the penalty coefficient whose value is greater than 0, and this value you will see when it is in the feasible region, that value is also greater than 0. Okay? And this f of x is what? That each term summation of f, that is what is called summation of minus 1 by g j of x, that is the f of x. Repeat, summation of j is equal to 1 to m minus 1 by g j of x is the f x. Check this one. If it is satisfied, stop the iteration. Otherwise, you go to the next step. Otherwise, go to the next step. So, step 4. When you go to the step 10, update your penalty function coefficient c. When XTR function method, I told the value of c is greater than 0, the value of c is greater than 0, and most probably it is a greater than 0 and less than 1. Say c is equal to, we consider 0.1. Now, we are decreasing this value with by 1/10. That we have seen why you are decreasing this one. It is the feasible region which is far away from the boundary of this feasible region, it will approach to the near the boundary when you do like this way. So, that things, and set k is equal to k plus 1 and go to step 2, and step 2 is this one. You start the iterative process once again, this one, and in this way you will do until and unless this condition, stopping criteria condition is not satisfied, either one of this is not satisfied. So, this way the interior penalty function method or barrier function method is solved. Agree? And these two methods are efficient in solving the nonlinear, what is called optimization problems. Then we will see next that how to solve a problem by taking a numerical example, employing the technique what we have discussed, the interior penalty function method or barrier function method. So, I will stop the lecture here only.